Okay, so chapter 33 is about electromagnetic waves. You want to go to Canvas and click on the modules and click on find the folder, subfolder that says chapter 33, and there's a lecture notes, this one that you can read, and also the lecture I'm recording right now. So electromagnetic waves are the intro to optics. So we need to know, what exactly are electromagnetic waves. So before we start this, slide, I want to show you the Maxwell's rainbow. So let me stop sharing and let me share another one. Just give me a second. Okay, so electromagnetic waves. So this is the if you look at this, these are the electromagnetic waves that covers that shows the frequency range and also the wavelength range. And the focus of this physics 214 will be on the electromagnetic waves in the visible spectrum, which we call light. So you can see that these are the electromagnetic waves with a frequency that is within the range that our human eyes can detect, can actually discern the colors. So you can see that it range from blue all the way to red and things like that. So you can see that the other thing I want to draw to your attention is that if you look at the wavelength, the wavelengths right here is about like let's see, it's about like 480 all the way to like 650 or 670 that we can our human eye can detect, and also you can see that when there's a shorter wavelength, the frequency is higher. Okay, and when we have a long wavelength wave, then the frequency is actually lower. And what are the waves? What are the electromagnetic waves that have long wavelength and low frequency? You can see that radio waves, microwaves. These are the waves that have long wavelength, meaning that they have a lower frequency. And these are the waves that have lower energy, which you're going to learn in later chapters. If you look at the short range, waves, what are the waves that are short range, short wavelength that has a higher energy and high frequency? What you see here is a gamma ray, X-ray, ultraviolet. That what we are all aware that they are high energy waves. They also have short wavelength and they have high frequency. Anyway, so these are the electromagnetic waves that covers different kinds of waves, and we are going to focus on the visible light, which is in this range. Okay, so now let's go back to the slides. So let me change slideshow. Okay, from the beginning. All right, that's not what I want to do. Okay, hold on. Let me share this. Okay, so let me start from the beginning. Let me see if I can do that. All right. Okay, so you can see that, chapter 33, we're going to spend the first part of this recording on the property of electromagnetic waves. So let me scroll down. So electromagnetic waves, what are they? They consist of electric field and magnetic field. So that's why we call that electromagnetic waves. And they can be generated using the induction law. If you remember in physics 212, you learn you learn the Faraday's law of induction. You also learn the Maxwell's law of induction. So we're going to actually briefly touch upon what those how the electromagnetic waves are generated. Suffice to say that you have an energy source, and there's a RLC oscillator, and then LC oscillator that generate waves. And with the inductor and a capacitor, magnetic field can change, electric field can change. And what we found is that when magnetic field changes, then electric field will be induced. And when the electric field is changing with time, we found that magnetic field will be induced. And so you can see that when one changes, the other one will be induced. And when the other one be induced, meaning that it changes with time, then the other quantity is going to be induced. And so through this bootstrapping process, then the electromagnetic field are produced. Okay, so and then you can see that they just generate this traveling waves. So as I mentioned, electromagnetic wave consists of electric field and magnetic field. So we can actually use this expression, use this two expression to indicate how the electric field and the magnetic field changes with time. So the other quantities, so this E and B, they are a function of time. So if you want to write it out, you would say that it's E of t that's equal to amplitude times sine of kx minus omega t. Likewise, magnetic field can be expressed by the maximum value and amplitude and then times sine of kx minus omega t. So you can see that electromagnetic waves can be described by a sinusoidal wave. And the K here is what we call the wave number, which is, so your K, if you remember, your K is equal to 2 pi over the wavelength, okay, of the wave. And so it's what we call the wave number. And omega is basically equal to 2 pi times the frequency. So it's actually what we call the angular frequency, okay? And we also know that that just equal to 2 pi over the wave periods. Okay, so, and the other thing that we want to look at this is that you can see an electric field and a magnetic field, they have exactly the same expression. They are in phase, meaning that the argument within the sinusoidal form are exactly the same. So we call that they are in phase, and but then they oscillate in different direction. Okay. And the speed of light is, can be calculated for any waves. Speed of light can be calculated using omega over k. Okay, so this is the expression that applies to every situation when you're dealing with a wave. But when you're dealing with the electromagnetic wave, we know that the speed of light, the wave speed is what we call the speed of light, and it has an expression which we're going to actually touch upon, which is equal to 1 over mu naught epsilon naught. You probably can see it, but I actually cannot see because it's blocked by my the functions of Canvas. I'm sorry, the Zoom. So anyway, so this is the expression which is the mu naught times epsilon naught. If you recall, mu naught is a quantity associated with the magnetic field. Epsilon naught is a quantity associated with the electric field, and one is called the so epsilon naught is called permittivity constant, and mu naught is called permeability constant. So those constant value, you can just Google that or just look them up in the textbook. Okay, so we found that the speed of light is actually a fixed number. It has this value. So we usually just say that it's 3 times 10 to the 8th meter per second. So instead of using this whole number, you can just say that is, we can approximate it to be 3 times 10 to the 8th meter per second. And we've known that speed of light does not change, does not change. And this is the, I wouldn't say it does not change, but the maximum value of the speed of light is 3 times 10 to the 8th, okay? And so what are the properties of electromagnetic waves? What we know is that electric field is perpendicular to magnetic field. So they are both oscillating, but they both oscillate in a perpendicular way, okay? And also, because let's say if this is electric field oscillating in this direction, and your magnetic field is into and out of the page, okay? So electric field is oscillating up and down, and magnetic field is oscillating in and out of the page. Then then when you do the E cross B, so point your fingers in the directions of electric field, okay, upright, and then you sweep your finger toward the magnetic field, which that clockwise, kind of clockwise. When you do that, when you do this E cross B, okay, so these are your fingers, and then you curl your finger, toward you. Then your thumb is going to give you the directions of wave direction. So this is the propagation directions of wave E cross B. So electric field, magnetic field perpendicular to each other. E cross B gives the wave direction, and E and B, they each vary sinusoidally. Okay, and I don't know. Let me see. Can I? to this. Okay, so I'm going to scroll down to the next page. Okay, and then so this is the way to show to show you how the electric field and magnetic field, they are how they relate to each other. So like I mentioned, electric field is oscillating up and down. Magnetic field is in and out of the page. So when you do the cross product, E cross B, this is the directions of wave propagation. Okay, and the wavelength, of course, is from peak to peak. That gives you the wavelength of the wave. Okay, and what we found is that the ratio of electric field to magnetic field, either in the instantaneous value or the maximum value or the amplitude, they always give a fixed number, and that fixed number is what we call the speed of light. So the speed of light, as I mentioned earlier, is 3 times 10 to the 8th meter per second. It is the maximum value that of the electromagnetic wave. Speed of light does change. It can only get slower. Okay, and this 3 times 10 to the 8th meter per second refers to speed of light traveling in air or traveling in a vacuum. But then if the electromagnetic wave is traveling through water, if it's traveling through glass, we know that speed of light will actually be smaller than 3 times 10 to the 8th meter per second. It's actually, it will be smaller, okay? Right, so this tells you that, to find the speed of light, you can either use the amplitude ratio, or you can use the instantaneous value of the ratio, or the previous expression is 1 over square root of the two constants. Okay, so as I mentioned, electromagnetic field, they are produced by the low inductions. So when the magnetic field changes with time, because it's sinusoidal, so when it changes with time, it induces electric field. So that's via the Faraday's law induction, and so when the electric field changes with time, because is a sinusoidal form, then induces magnetic field, and that's via Maxwell's law induction. And that's why they each continuously create each other through via the induction, and so they generate the propagating electromagnetic wave traveling space. Okay, and then the next page is briefly. I just want to briefly touch upon this, just to give you some perspective, about how the electric field is produced and how the magnetic field is induced. Okay, and this is the Faraday's law induction, and this equation tells you that when the magnetic flux changes with time, it's going to induce the electric field. And when you integrate electric field along the closed loop, then this equation, it must, follow this expression, and there's a negative sign in front of it. Okay, and so in other words, we can actually look at, this loop, and that's a electric field again is oscillating up and down. Magnetic field is oscillating in and out of page. And when it's oscillating, magnetic flux is going to change with time. So we know that this is a non-zero. The flux, will change with time. Flux is flux. Magnetic flux is the magnetic field times the area, right? So you can actually integrate along this closed loop. Okay, let's say this has the height of h, the length has height of h, and this has a length of dx. So you can integrate, follow this loop. So you can have integrate electric field along this closed loop. And what we found is that on this side, you have the E plus dE and then times H, right? Because it's E dot ds. So let's say this is kind of clockwise. So you have that, and then on this side, because the electric field and the displacement are perpendicular to each other. So when you do the scalar product, it will give you 0. So no contribution on this length, and no contribution on this length. And on this side, your H is downward, but the electric field is upward. So you will have, when you do the scalar product, that will be minus EH. So the net result when you evaluate this will just be H times dE. Okay, the increment change of electric field. And then for the magnetic flux, we know that it is magnetic field times the area. So what is the area? The area for this box area, that will be h times dx. So there you can actually just set them equal to each other with the minus sign. So you have the h on the left hand side, it is HDE. On the right hand side, that is your this is your magnetic flux. And then the time the time rate of change of magnetic flux is HDX and then dB dt. Okay, so then you will have you set it equal to each other, and then there's a minus sign in front of it, and then so you can rearrange this, divide dx on both sides. You have the d and h just cancel out. So you have the dE over dx that's equal to negative dB dt. So what you have here is that this is for one dimension. This is just in one dimensional. That's the electric field. Can change in x, y, z. So you have the partial E partial x that's equal to negative partial B partial t. So what this equation tells you is that when the magnetic field changes with time, which we know that it will because it can be described by a sinusoidal form, then the electric field is going to be induced and it will advance in space because it's partial E partial x. Okay, so I kind of give you some idea about how the electromagnetic field are produced just based on lower Faraday's law induction. Magnetic flux changes, then it will induce electric field. And by the same token, we can apply that to the magnetic field. And from the Maxwell's equation, we know that dBds, when you do a closed loop, is equal to mu naught xo naught and then dE over dt, magnetic electric field flux over dt. And you would perform exactly the same evaluations of this. You have the BDS for that, and then again, the magnetic field and this part, they do not contribute because they are perpendicular to each other. The only two terms that will contribute will be this term times h and then this term times h, and then suffer by minus sign. And then for the magnetic flux, that will be electric field times electric flux. That'll be electric field times the area. And so you will get exactly the same same as that the changing magnetic electric field is going to produce or induce magnetic field. Okay. Oh, so this part basically says, this is from previous slide. So you have the partial E partial X. You can just substitute your E with the sinusoidal form. So when you do partial E partial X, you will get the K amplitude, and then sine becomes cosine kx minus omega t. And when you do the partial B partial t, you'll get the negative W magnetic field amplitude and then cosine kx minus omega t. So when you set them equal to each other, and then there's a minus sign in front of it, from previous slide, you'll get that they have both have the cosine, so they cancel each other. So what we have here is that the electric field, the ratio of amplitude is equal to a fixed number, which is the speed of light. Okay. So and likewise, this is actually from the Maxwell's law induction. So we pretty much you just follow the same thing, and you will get this, and then the final equation is this. This equation tells you that when the electric field changes with time, there's going to be magnetic field induced that will advance in space. Okay, and so again, if you just substitute B with the Bm sine of kx minus omega t, and then evaluate partial B partial x, and do the same thing, evaluate partial E partial t, and set it equal to each other. Then again, this two cosine canceled, and then you will find that Em over the amplitude ratio is equal to, after you arrange this, is equal to this. And we know that omega omega over k is equal to c. So this equation is equal to this, and then you will get that the c is just equal to square root of mu naught times x naught. Then that's how we derive it. Okay, because this from previous slide we know that it's equal to c. So your c squared is equal to this, and so that you get your c here. Okay. So that is that's basically the how we know the property of electromagnetic wave. They each will produce each other. They propagate in time and space. And they they are perpendicular. Electric field and magnetic field are perpendicular to each other, and the cross product gives you the directions of wave propagation direction. Okay, and the speed of light can be found by 3 different methods. It's either the amplitude ratio or instantaneous value of E to the ratio of instantaneous value of electric field to magnetic field, and also it is equal to 1 over square root of mu naught times x naught. So we know that you have the electric field, and it can propagate through space, and it changes with time. So one of the things that we want to really interested is that how much energy is actually carried by the electromagnetic field. And to quantify that, we define a quantity which we call our Poynting vector. And the Poynting vector, we use a capital S to indicate to represent that. So what is a Poynting vector? Poynting vector, by definition, is the rate of energy transport per unit area. Rate of energy transport is power per unit area. That is, let's say you have the area, you have the electromagnetic wave passing through this area. So what is the power per unit area? Okay, and that is what we call Poynting vector. So what is the expression for Poynting vector? Is actually equal to 1 over mu naught E cross B. Remember, E cross B give you the directions of wave propagation. So if the wave is propagating along the right, in the rightward direction, this is the directions of this is the directions of energy transport, and electric field is is oscillating in this direction. Magnetic field is oscillating in and out of the page when you do a cross product. This is the directions of wave propagation. Okay, so everything is consistent, and so the unit for Poynting vector, of course, is power, which is in watts over meter square. And so when we do this, so this is definition of Poynting vector, the rate of energy transport per unit area. So we can actually like evaluate E cross B. Now we know that E and B are perpendicular to each other. So E cross B just give you EB sine of 90 degrees. Sine of 90 degrees, of course, give you 1. So you have your S, the magnitude is 1 over mu naught E times B. Okay. And we know that the ratio, C is equal to E over B. So this expression can be, if you replace your B by E over C. So this one will give you another expression, which is 1 over C mu naught times E squared. Now here, the E and B are instantaneous value. It's not the amplitude, okay? So you can see that the rate of energy transfer is a function of time because it is not a fixed value. Electric field is going to change with the time, magnetic field is going to change with time. So when you do the cross product, it is also going to be a function of time. Okay, and so so if this is a function of time, it's going to change. It's going to change with time. We are also interested in knowing what is the average value of the of energy transport per unit per meter square. So we call the quantity, the time average value of the Poynting vector to be the intensity I. So in other words, the intensity of I, the energy, what is intensity of energy through, through this space will be the, will be the average value, time average value of the Poynting vector. So we need to evaluate this quantity. The bracket indicate, the time average over the period. Okay, and mu naught, of course, is a constant, so we can, bring it outside of that. And in fact, we're going to use this to do the time average, because we have the just the E squared. And if you remember, E is actually equal to the amplitude and then the sine square, right? So pretty much you're going to do what is the you're going to evaluate what is the sine theta square over the period. Theta here is kx minus omega t. Okay, so so that is when you do the time average, that gives you the intensity, and that is equal to 1 over c mu naught, and we are evaluating the electric field square, and then the electric field, this is the instantaneous value, this is the amplitude times sine of. So basically you'll just be evaluating this because the amplitude does not change with time. Okay, so what is sine square? Sine theta square, when you do the time average, that actually gives you just 1/2. Okay, if you're familiar with the calculus, then a sinusoidal form, if the sine square, and when you do the time average, that just give you 1/2. Okay, so so then we will have, so our intensity, you will get this value. You have 1 over c mu naught, and then because that's 1/2, and then the amplitude square. And if we recall, the root mean square value is defined for every root mean square value is defined as the amplitude over square root of 2. So we have the square here. So the whole thing here is square. And you can see that the EM square over 2 just give you the root mean square square. So your intensity is equal to 1 over c mu naught and then root mean square value. So in other words, if we want to know what is the intensity of the electromagnetic wave, then that will be 1 over c mu naught and the root mean square value of the electric field square. Okay, so so this tells you that when you have an electromagnetic wave propagating through space, it's going to carry energy, and this is the amount of energy, the rate of energy transport per unit area. Okay, and this is the how you found that. And if you remember, back in physics 212, when you learn electric field, when you learn magnetic field, we know that each quantity, electric field and the magnetic field, they are going to store energy. Capacitor is the device that store electrical energy, and the inductor is the device that store magnetic energy. So we know that electric field, so energy can be stored in the form of electric field or magnetic field. And you also, if you remember in physics 212, you also learned that there's what we call the energy density, and there's an electrical energy density, which is 1/2 mu naught xo naught E squared. And so if we replace E by CB, from previous slide, then we know that it's equal to 1/2 xo naught CB squared. And we can further, expand, your CB, and C is equal to, C is equal to 1 over square root of x over mu naught. So when you square it, you got that, and you got that, and then this get canceled. So you got B squared over 2 times mu naught. And what is B squared over 2 times mu naught? That is just the magnetic field and magnetic energy density. So what this equation tells you that energy is actually the amount of energy stored in the electric field is exactly the same as the energy stored in the magnetic field. So mu E is equal to mu B when you're dealing with electromagnetic waves. Okay. All right, so that's basically what they carry equal amount of energy and being transported through the space. Okay, and so when we talk about energy, let's say this is the source of the energy, and then the energy, when the gravity, so when the electromagnetic wave propagates through space, energy actually the intensity will decrease in space. Okay, we already know that the intensity is going to decrease in space. The farther away from the source, the smaller the intensity. So they pretty much follow 1 over r squared rule. Okay, so this is just think about as in 3-dimensional, and you have the source right at the center, and and the electromagnetic waves propagating through space in the spherical in 3-dimensional, And so the farther away from the source, the smaller the intensity, and it follow the proportional to 1/r squared. So so the equation, which is actually I can't see here, but is basically equal to the power at the source at the center, okay, over the area, and the area for spherical shell is 4 pi r squared. Okay, so farther away, the smaller intensity until you know it has very low intensity when so far away. Okay, so oops, sorry. Right, let me see. Okay, so okay, so the next thing I want to talk about is about the radiation pressure. We know that electromagnetic wave will carry energy, you know, with them. In addition to that, electromagnetic waves carries momentum, and you know, momentum and force are related to each other. And so, so where does that and then force and pressure are related to each other as well. Okay, so this is just for your information that you know, electromagnetic wave carries momentum, and so when it travels through space, there's what we call a momentum change, which we call delta p. P is the linear momentum, and delta p is the change, and that's going to relate to the energy change. So U here is the energy of the waves. So how do we find the momentum change? The momentum change for the electromagnetic wave is equal to the energy change over the speed of light. Okay, so this is like when you have a you know, let's say this is you know, this is ground, and you have electromagnetic wave that's propagating and hit the ground, and you know, what is the momentum change? So if the you know, if the energy is being if the total energy is being absorbed by the ground, then this is the you know, this is how you calculate the momentum change, which is the energy change over the speed of light. What about when you encounter the surface that all the light rays actually being reflected off? Nothing is being absorbed, it's being reflected off, then we know that the change in momentum has to be twice, because you know, this is one change and this is another change. So so for total reflection, then you know, then the momentum change will be 2 times delta U over C. Okay, so this tells you that when you have you know, electromagnetic wave momentum, there's a momentum change. In addition to that, there's what we call the radiation pressure. So what is the radiation pressure? Pressure, like as I mentioned, pressure and force are related, and momentum and force are related. So 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 suffice to say that the PR here indicate the radiation pressure. So this is a force. So just imagine that when you have electromagnetic wave impinge on the ground, there's a you know, there's a momentum change. We know that force and momentum change are related by Newton's second law, if you remember. Okay, so the time rate of change of linear momentum give rise to the force. So force and linear momentum are you know, are related by this, and the energy, the amount of energy, you know, how do we you know, so that's a you know, when it hit on the ground, there's energy change. How do we find the energy? The energy, of course, if we know the intensity, then if we know the area, if we know the time, then you can actually calculate the delta U, which is the intensity times the cross sectional area times the time, right? Just by definition. And so the total absorption, we know that total absorption is this expression. So you have the delta U over C, and so so this is the momentum change. And so momentum change is this, and we know that force is equal to delta P over delta T. So we can actually divide delta T here. So delta T just you know, cancel out. So you have the force, which is I intensity times the area over the speed of light, and the you know, the pressure. So when there is a force, there's a pressure. How do we find pressure? Pressure is actually you know, force over the unit area. So you have the I A over C, and then divided by A, that gives you the pressure. So what we found is that the radiation pressure is intensity over the speed of light. So what does that mean? It means that when there's an electromagnetic wave impinged upon the surface, this surface actually experiences a pressure from the electromagnetic waves. And if this is a total, total absorption, then then you will have a magnitude of I over C. If it is total reflection, then it will be twice of that. Okay, so the radiation pressure is I over C for total absorption, and 2 times I over C if that's total reflection. And so that's why when you on a snowy day, higher temperature of course will get the snow melted. But if you have a sunny day, then all this electromagnetic wave or photon, which you're going to learn, the photon impinge on the ground, and that comes with the pressure. So that pressure is actually gets the ice melting even faster. Okay, so and that's because of the pressure. Right, so that concludes the first part of chapter 33, and there's going to be a recording the rest of the chapter 33. Okay.